All right, in this segment we're going to be looking at another basic resistive circuit configuration, which is useful. This is going to be the resistive linear combiner. Okay, in this situation we're going to have n input voltages that couple into a common node through some resistors. So we have, let's say, something like this, where we have V1 ... down to V sub n. And we've got some resistors. Actually, we're going to use conductances for this one because it makes our life a little easier here. So we have G1 ... down to G sub n. And there's an output voltage, V out. And there'll be some current flowing out of each voltage source, I1 ... down to I sub n. And those currents will combine at this common output node here. And we're interested in figuring out how does the output voltage depend on these n input voltages. Okay? So, well, what do we know? We know for all I, we have an Ohm's law relationship, right? So I sub I is equal to G sub I times the difference between VI and V out. Okay, so remember, current flows from high potential to low potential, right? So there's a voltage drop across resistor I of an amount is basically the voltage VI minus the voltage V out. So this is our voltage difference. Maybe it's hard to say what to call it. VR1, and then this would be VRN, something like that. So we're going to have V sub I minus V out, and this is what we've called here V sub Ri, the voltage drop across the ith resistor. Okay, so this is Ohm's law in its conductance form. Normally we say V equals IR, but we can also say I equals G times V. And sometimes that expression makes our life somewhat easier. It would also have made our life somewhat easier in the current divider case, but this one is especially nice to do in terms of conductances. So we also know that KCL at the common output node tells us something at V out. It tells us that the sum of the currents flowing into this node has to be 0. So all of the currents here are flowing by hypothesis, the way we've set up our sign convention here. They're all flowing into this node V out. So we have I1 plus ... plus I sub n. Zero amps. And so we can substitute our Ohm's law expressions into our KCL. So if we take this down here, we can find that we have G1 times V1 minus V out plus ... plus G sub n times V sub n minus V out equals 0. And we can distribute the GI into its own parenthesis, and we can collect all of the terms involving V out onto the other side of this equation. And so that doing that would give us G1 V1 plus dot 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 plus Gn Vn is equal to G1 V out plus dot 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 Gn V out. We can factor out that common V out, and we probably like to put the V out on the left-hand side, so if we flip the left and right sides of the equation around and factor out that common V out, we have V out is equal to, or V out times G1 plus dot 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 plus G sub n is equal to G1 V1 plus dot 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 plus G sub n V sub n. And we can divide through by this thing in parentheses here to solve for V out. V out is going to be equal to, I'm going to call this, let's say W1 V1 plus dot 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 plus W sub n Vn, where Wi is equal to G sub I over G1 plus dot 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 plus G sub n. Okay, so what we have here is V out is a linear combination of the n input voltages. So there are weights, it's a weighted summation. So there are weights on each input, and those weights are determined by the conductance through which that input couples into the output node, and it's normalized by the total conductance we would see if we were to sit on this node and look back toward the inputs. So conductances combine for parallel resistors, like resistors combine in series just by simple addition. So this, if you like, we could also write as G sub I over some G total, the total conductance seen looking back here, which is just the sum of these n conductances. This is very similar to the current divider ratio expressed in terms of the conductances. Notice that these weights all sum to 1, right? Because if we add up all the weights for I equals 1 to n, we would get in the numerator G1, the sum of G1 up to Gn. In the denominator, it's normalized by that same sum so that these weights all sum to 1. Okay, but this is a linear combination of the input voltages, and that's often a very useful sort of operation to be able to do. So you find this kind of configuration in things like summing amplifiers, where you have a bunch of input signals we'd like to add up, like in an audio mixer, that kind of thing. An important special case would be the case of two inputs. So we have a two-way, this would be an n-way linear combiner. We have a two-way linear combiner. So for a two-way case, we'd have just, V1, let's say it's V in, and some reference voltage, maybe. So we've got an R1 and an R2, and we just have V out is equal to, we could call it well, say W1 Vn plus W2 Vref, where W1 is equal to G1 over G1 plus G2, and W2 is equal to G2 over G1 plus G2. Okay, but G1 is 1 over R1, and G2 is 1 over R2, so this is equal to 1 over R1 times 1 over R1 plus 1 over R2. And so 1 over R1 plus 1 over R2 is just R1 parallel R2, and we're left with a 1 over R1 upstairs, and so that's R1 parallel R2 over R1. Likewise, we can write this as 1 over R2 divided by 1 over R1 plus 1 over R2, and so this is R1 parallel R2 over R2. So you can see that these are pretty much just like the current divider ratios that we would have in a situation where we had two resistors or something like that. So these weights behave that same way. And we could draw a voltage transfer characteristic, let's say, V out as a function of V in, and we could maybe have a couple of different values of Vref, so Vref 1 and Vref 2, and we can draw here for reference the identity line V out equals V in. Okay, so this has a slope of 1, and that lets us put in here on the y-axis where Vref 1 is, and also where Vref 2 is. And what this relationship is it's basically just a straight line with a slope of W1 and some y-intercept. Well, if we make V in equal to Vref, then because W1 and W2 sum to 1, then if V in is equal to Vref, we know that V out is also equal to Vref. And so the two voltage transfer curves here would have a slope of W1, and they would go through the identity line at Vref. And so for these two different values of Vref, we would have these two different voltage transfer curves and the slope of W1. So these lines would be parallel to each other, and they would just shift as Vref shifts. So that's the resistive linear combiner. Okay, so for the rest of this segment, I want to start developing an idea which will allow us to think about how component tolerances affect our circuits. And so to develop this notion, we're going to need something called a tangent plane approximation. Okay, so these things like the current divider ratios or the weights on our resistive linear combiner, or maybe the gains on our amplifiers or something like that, are functions of our parameter values, like our resistances, sometimes capacitances, and they in general are going to be nonlinear functions of those parameters. And so what we would like to know is that for small changes in values of those parameters, how does that affect a given output? And so what we're going to do is we're going to model some parameter of interest in our system, y, as some function of a bunch of parameters. So let's say call them x1 dot 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 up to x, maybe x sub n. And we're interested in what happens if we make small changes in these parameter values about their nominal values. And so we want to know how do those changes affect the output parameter y. So we're going to have some y plus some little delta y is going to be equal to f of x1 plus delta x1 up to x sub n plus delta xn. Okay? So you may have seen this, you may not have seen this in calculus. That's fine. This is not a math class, but we will be using some math. But you certainly probably have seen this in one dimension. So this is going to be, if you like, if you've only seen this in one dimension, this is going to be, if you like, an n-dimensional generalization of Taylor's theorem, okay, where you can take a nonlinear function and you can expand it in a infinite series of powers of x, a polynomial. And so this is going to be equal to, by sort of an ND Taylor theorem, give myself a little more space here. This is going to be equal to the function evaluated at its original point, x1 up to xn. And then there's going to be a term that involves first order partial derivatives. So this would be like the linear term, I equals 1 to n of df dxi times delta xi. So this derivative is evaluated at the original point. And then there'll be a second order term, 1 over 2 factorial times sum over I equals 1 to n, sum over j equals 1 to n. And then we have the second order mixed partial derivatives, d squared f d xi dxj, and then we've got the products delta xi, delta xj, and so on. And then there's a third order term, 1 over 3 factorial, sum over I, j, k, and then we've got the third order, blah, blah, blah. Okay, so this is an infinite series. We don't even really care what this exactly looks like. What we're going to say is that for sufficiently small delta x's, these higher order terms don't matter. So this is for sufficiently small delta xi, we can approximate this as just the first order term, the constant term plus the first order term. So we get f of x1 up to xn plus this first order term I equals 1 to n of df dxi times delta xi. Okay? And so we can, of course, subtract off our original equation. So we can subtract a y from the left-hand side, and we can subtract the f of x1 to xn off on the right-hand side, and just have an equation for our change in y. So it says that delta y is approximately equal to the sum from I equals 1 to n of df dxi. Now, this is evaluated at x1 to xn, right? So evaluated at x1 times delta xi. And this is the tangent plane approximation. This is basically just like saying I can take a nonlinear curve, and for a sufficiently small neighborhood around a given point, I can approximate that curve as a straight line where I take the slope of the tangent line to be given by the derivative of the curve at that point. This is just saying the same thing, only instead of being for a straight line, for a curve. This is for a curved surface, and instead of having a straight line, we have a plane, hyperplane in n dimensions. Okay, so we're not talking necessarily here about spatial coordinates. We're talking about some sort of parameter space where these this y could be, let's say, one of the weights in our linear combiner that we just talked about, and these x's could very well be the resistor values or the conductance values. Okay, they have some tolerance. They might be made from 1% resistors, and so there may be some sort of statistical model of how these delta x's behave, and we're interested in how do those combine eventually to change the parameter of the system that we care about. That's kind of what we're interested in modeling here. Okay, so this is the tangent plane approximation. And so the next thing we're going to do is we're going to talk about something called per unit variations. Okay, this is like a normalized change, like a percentage change in some parameter. Okay, so per unit variation. So this is basically delta y over y. It's just the variation in y divided by the value that y has. And for sufficiently small changes in our parameter values, this should be equal to sum I equals 1 to n. We're just dividing the right-hand side by f, 1 over f times df dxi times delta x sub I. Now, we can do some things on this. So we know that 1 over f times df dxi could be written, since the derivative of log of f is 1 over f, and then we apply the chain rule to get the derivative with respect to xi, we could rewrite this as sum I equals 1 to n of d by dxi of log of f times delta xi. Okay, so that's expressing our per unit variation in y in terms of something called a logarithmic derivative. And now we'd also like to have this, at the end of the day, per unit variation in y as a function of a per unit variation in the parameters. So we need to get a 1 over x sub I in here. Well, we can always put something like that in by multiplying by 1 in a convenient form. So this would be multiplying and dividing by xi. Now we're assuming here xi is not 0. But what we can do is then group the 1 over xi with the delta xi and write this as the sum from I equals 1 to n of xi, this is the one from upstairs over here, times d by dxi of the log of f times delta xi over xi. So this is an equation that relates the per unit variation in some parameter y to the sum of, or a weighted sum of, the per unit variation in each of the parameters that y depends on. And this thing has a name. This weight has a name. It's denoted by S super Y sub xi, and this is the sensitivity, per unit sensitivity of y with respect to x sub I. So Sy of xi can be written as basically xi times d by dxi of log y. And if we do one step out on this logarithmic derivative, we can rewrite this as xi times 1 over y times dy dxi. Right, so this would be xi over y times dy dxi. And you'll sometimes see it like this, and you'll sometimes see it like this. Okay, so we want to take a look at the use of this concept of per unit sensitivity in thinking about different scenarios. But let's take a simple example of this. Suppose we have an equivalent resistance, right? So we know that if we have n resistors in series, we have R1 up to R sub n connected in series, and this is equivalent to some equivalent resistance Req, which is R1 plus ... up to R sub n. And what we want to know is what is the sensitivity of the equivalent resistance with respect to each resistance. Well, that's just equal to Ri times d log Req by d Ri. Well, that's just Ri over Req times d Req d Ri. Well, Req is just the sum. They each have a weight of 1 in the sum, and so that derivative is just 1. So the sensitivity is just R sub I divided by Req. So if I have n equally valued resistors that each make up, say, 1 over n of the total resistance, then each one would have a weight of 1 over n. So its variation would contribute equally to the overall variation in the equivalent resistance. But what if I have a situation where I have one resistance which is, say, very large, and the other one is very small? Well, let's suppose I have a situation where I have a 499 ohm resistor, which you've probably all wondered why isn't there a 500 ohm resistor in the standard values. 499 is the closest 1% resistor value to 500. What if I want to make a 500 ohm resistor by putting a 1 ohm resistor in series with my 499 ohm resistor to make a 500 ohm resistor? And suppose I want to make a really precision resistor. Like I want that 500 ohms to be really close to 500 ohms. And so let's say I want to make it 0.1%. Question is, do I need to use 0.1% resistors for each of these two resistors to get 0.1% for my 500 ohm resistor? Well, that might strike you as kind of a funny thing to wonder, but 0.1% resistors cost maybe 10 to 50 times more than 1% resistors. So suppose I wanted to reduce the amount of cost of my bill of materials for some circuit design that I'm working on. Do I need to make these both 0.1% resistors to get the 500 ohms within 0.1%? Well, according to this result, my 499 ohm resistor, the variation or the sensitivity of the 500 ohms with respect to the change in value from 499 ohms is going to be 499 over 500. That's the weight. So very close to 1. So the sensitivity for the 500 ohm equivalent resistance with respect to the 499 ohm figure on the nominal value on the 499 ohm resistor is going to be weighted by almost 1, 499 out of 500. And so I better make that a 0.1% resistor. What about the 1 ohm resistor? That 1 ohm resistor is going to be weighted by 1 ohm out of 500. And so that's a completely different story. That's going to be knocked way down by a factor of 1 over 500. Right, so I could even put a 10% resistor there and have that knocked down by 1/500th, and I'd probably be okay. But certainly a 1% resistor being knocked down by a factor of 1 over 500 is going to mean that I'm going to be much less sensitive to variations in that 1 ohm resistor with respect to my overall 500 ohms. So I could use to get 0.1% tolerance, I could probably use a 0.1% resistor here, and I could probably use a plus or minus 1% resistor here. Okay, and we'll develop a few more examples of this idea in the next segment, and talk about how these sensitivities combine to actually think about different senses of the tolerance of some component, like say this equivalent resistance or something like that. Okay, we'll see you next time.